Have you ever wondered what non-regular languages are in the theory of automata? Today we delve into this captivating topic. Non-regular languages in the realm of automata and formal languages are languages that finite automata cannot recognize. They are more complex than their regular counterparts and demand more powerful computational models for their recognition and description. Let's take a sneak peek into some examples of non-regular languages. First off, we've got context-free languages, or CFLs. Think of these as a level above regular languages in terms of complexity. They are defined by context-free grammars and are recognized by push-down automata. A good example of context-free languages would be languages with nested structures, such as balanced parentheses or nested expressions. Next in line is context-sensitive languages, also known as CSLs. These are a notch higher than context-free languages in the complexity scale. They're not recognized by push-down automata, but can be recognized by linear bounded automata. Context-sensitive languages have rules that depend on the current symbol being read and its context or neighboring symbols. An example of this would be languages with palindromes of even length. Then we have the recursively enumerable languages, also known as REs. These are the most general class of languages in the Chomsky hierarchy and can be recognized by Turing machines that may not halt for every input string, but will eventually accept all strings in the language. And finally, we have languages that do not fit into the context-free category but are also not context-sensitive. These languages fall into an intermediate complexity level between context-free and context-sensitive languages. Understanding non-regular languages is crucial to the study of the hierarchy of formal languages and the computational complexity of problems in computer science. They represent classes of languages that require more sophisticated computational models for their description and recognition. Non-regular languages require more than just finite automata to be recognized. Let's explore why. First up, we have context-free languages, or CFLs for short. These are a fascinating category of non-regular languages, stepping up the complexity from regular languages. So what sets context-free languages apart? Their defining characteristic is the ability to include nested structures within the language. This may sound like a bit of a brain teaser, but consider the language of balanced parentheses. In this language, every opening parenthesis is matched by a closing parenthesis. This is a perfect example of a context-free language because the structure is nested and balanced. Context-free languages aren't just about parentheses, though. They encompass any language with similar nested structures. This could include nested brackets or expressions. These languages are more complex than regular languages and require a more powerful computational model to describe and recognize them. How do we recognize these context-free languages? We use something called a push-down automata. A push-down automata is a type of machine in the world of automata theory that's capable of recognizing context-free languages. It's like an upgrade from the finite automata used for regular languages. Now, how about describing context-free languages? For that, we use context-free grammars. These grammars provide a set of production rules for strings in a language. Each rule in a context-free grammar has a single non-terminal symbol on the left side and a string of terminals and/or non-terminals on the right side. It's these grammars that give a formal description of the structure of the strings in a context-free language. So, to recap, context-free languages are a type of non-regular language that can include nested structures. They are recognized by push-down automata and described by context-free grammars. This makes them a step up in complexity from regular languages. But it's this complexity that makes them so interesting and important in the world of automata theory and computer science. CFLs, with their nested structures, are a step up in complexity from regular languages. So strap in as we continue to delve deeper into the fascinating world of non-regular languages. Next, we move on to context-sensitive languages, also known as CSLs. A step above the complexity ladder from context-free languages, CSLs introduce an intriguing twist. The rules of their formation don't just rely on the current symbol being read, but also on the surrounding symbols or context. Let's take a moment to understand this concept. Imagine you're in a library, reading a book. The way you interpret each word isn't just based on that word alone, but also on the words that come before and after it. Similarly, context-sensitive languages are formed by rules that consider the neighboring symbols. Now, you might be wondering, how are these CSLs recognized? The answer is through a computational model called linear bounded automata. Unlike push-down automata, which are used for context-free languages, linear-bounded automata have the ability to recognize context-sensitive languages. Think of it as a super reader who not only reads each word, but also comprehends the entire sentence. But what do these CSLs look like? Let's consider an example. A language that consists of palindromes of even length is a context-sensitive language. In this language, each string is of the form W#W circumflex R, where W is a string over 0, 1, asterisk. W circumflex R denotes the reverse of W, and hash is a special symbol used as a separator. Essentially, the second half of the string is a mirror image of the first half, separated by the hash symbol. This is a context-sensitive language because the formation of each string depends on its entire context, not just on individual symbols. In conclusion, context-sensitive languages add a layer of complexity to the world of non-regular languages. They delve deeper into the realm of computational linguistics, where the context plays a crucial role in the formation and interpretation of languages. CSLs, as you can see, depend not only on the current symbol being read, but also on its context. Now let's venture into the realm of recursively enumerable languages, or REs. Recursively enumerable languages, often abbreviated as REs, are a fascinating class of non-regular languages. Sitting at the most general end of the Chomsky hierarchy, they encompass a wide range of language complexities. What makes REs stand out is their ability to represent any computable problem or language that can be decided by an algorithm. In other words, if there's an algorithm that can decide whether a string belongs to a certain language, then that language is recursively enumerable. Now, how are REs recognized? Well, the answer lies in the powerful computational model known as the Turing machine. However, there's a catch. While Turing machines can recognize an RE, they may not halt for every input string. Instead, they are guaranteed to eventually accept all strings in the language. This characteristic of Turing machines is what allows them to handle the broad complexity of REs. Let's delve into an example to make this clearer. Consider the notorious halting problem. This problem involves determining whether a given Turing machine will halt when run with a specific input. The language of the halting problem consists of all encodings of Turing machine descriptions and input strings for which the Turing machine halts. This language is recursively enumerable. Why? Because a Turing machine can be designed to enumerate all possible halting configurations, but it may not halt for every input, reflecting the undecidable nature of the halting problem. So to wrap up, REs are a remarkable class of languages. They encompass the vast array of complexities that can be decided by an algorithm and are recognized by Turing machines in a unique, non-halting fashion. They serve as a testament to the expansive potential of computational models and the various problems they can solve. REs represent any computable problem that can be decided by an algorithm. Quite fascinating, isn't it? Finally, we come to languages that are neither context-free nor context-sensitive. These are known as non-context-free languages, and they hold a unique position in the realm of formal languages. They are more complex than context-free languages, but not quite as intricate as context-sensitive languages. So what makes them unique? Well, non-context-free languages possess a level of complexity that can't be accurately described by context-free grammars. For instance, consider the language represented by the expression a circumflex NB circumflex NC circumflex NN 0. This language cannot be described by a context-free grammar due to the nested nature of the strings. In these languages, the number of A's, B's and C's must all be equal, and in the same order. This sort of pattern can't be captured by a context-free grammar, which is why it's classified as a non-context-free language. These languages present a level of complexity that sits between context-free and context-sensitive languages. Let's take a moment to reflect on what we've learned today. Non-regular languages, unlike their regular counterparts, cannot be recognized by finite automata. These languages encapsulate a higher level of complexity and demand more sophisticated computational models for their description and recognition. We've journeyed through the intricacies of context-free languages, or CFLs, which exhibit nested structures and are recognized by push-down automata. We've tackled context-sensitive languages, or CSLs, which depend on the current symbol and its context, and are recognized by linear-bounded automata. We've also delved into recursively enumerable languages, the most general class in the Chomsky hierarchy, which can represent any computable problem or language that can be decided by an algorithm. And we've explored non-context-free languages, which stand as examples of intermediate complexity between context-free and context-sensitive languages. Understanding non-regular languages is crucial for studying the hierarchy of formal languages and computational complexity in computer science. Until next time, keep exploring.